stand here to share with you the results of a feasibility study that we carried out for characterization of the Vaca Muerta formation shale with post-stack seismic data and our attempts at reducing the uncertainty therein. First, I would like to acknowledge the authors of this work and presentation, namely Ritesh Kumar Sharma. I am the second author, and we both work for Arcus Seismic Solutions, TGS, Calgary. Our co-authors are Luis Fernando, Eduardo Trenchero, and Claudio Silvan from Pan American Energy, Buenos Aires. The Vaca Muerta shale that we are going to talk about is located in the Neuquén Basin in Argentina. Interestingly, the Vaca Muerta in Spanish, the name Vaca Muerta in Spanish means dead cow. The Neuquén Basin in Argentina was developed as a result of an extensional rifting in the late Jurassic, established between a back arc to the west, associated to the Sud-American plate, and a passive margin to the east. Subsequent deposition, thermal subsidence, and structural evolution led to the recognition of 5 different geographic areas in the basin, and these are, as you see listed up here, the thrust belt area to the west called thrust belt area to the west called the Malarque Agrio fold belt, northeast platform, embayment in the center, Huquen Wincul uplift joining the embayment to the south, and the Picun Lufu subbasin to the southwest. All these areas form the elongated northwest to southeast shape of the Neuquén Basin as we see here. The location of the area of interest is indicated by the yellow ellipse, and the formation of an interest is the late Jurassic, early Cretaceous Vaca Muerta formation. I'll be referring to it as the VM formation just for simplicity. It represents a regional and a drastic transgression that favored the anoxic conditions and helped preserve the organic matter. The contact between the VM formation and underlying Tordillo formation is distinct, and so we can pick it up on the seismic data. But the contact with the overlying Quintuco formation is gradual. For practical purposes, the overlying shale is usually taken as a single transgressive unit. Now, based on the subsurface data from the electrical and the acoustic log curves, mud logging data, as well as the borehole images, extensive facies studies have been carried out in the Neuquén Basin. It has been found that the VM formation comprises a variety of lithologies that include the organic rich calcareous shales, marls, carbonates, calcareous sandstones, and sandstones, whose proportion and stacking patterns they vary from the southeast to the northwest, and that follows the geometry of the deposition system. Different fault systems associated with different tectonic events that took place during the evolution of the basin disrupt the lower portion of the VM formation. And so, as a result, the natural fractures are present in different stratigraphic layers and affect the mechanical behavior of the reservoir. Now, the present available description of the VM formation, it is something like this, as I have tried to list up here. It is composed of the amorphous organic matter associated with the marine plankton and equivalent to the type 2 or 2s kerogen. With regard to the thermal maturity, the vitrinite reflectance RO varies from 0.8 to 2%, which is favorable. The TOC varies between 3 to 8% and is found to be higher in the lower parts of the VM formation. And the embayment area is inhabited with the light oil, that is 30 to 45 degree API, and is thermally mature. Similarly, the petrophysical analysis on the log data shows that porosities vary between 4 and 12% in the VM formation, and the lower portion has porosity between 8 and 12%, the upper one has between 4 and 8%, which is again very favorable. Now here I show ternary diagram which exhibits the mineralogical distribution of the VM formation in different paleogeographic areas, as we discussed earlier. The higher proportion of the brittle minerals, such as quartz and carbonates, is encouraging. Now, for a shale reservoir to become a successful shale play, the following characteristics, as you see up here, they are favorable, like the mineralogy. the organic richness, the maturation, thickness, and this thickness is more than the thickness that we see for the shale formations in other parts of the world. The porosity, permeability, the brittleness, and the oil and gas in place is huge in this area. And pore pressure and depth, they are all very favorable. And the optimum combination of these elements led to the favorable leads to the favorable productivity. Now, the borehole measurements such as the well log curves and geochemical analysis, as well as the measurements on cores and cuttings, they are some ways of directly estimating TOC. These methods are applicable only at well locations. But our goal is to characterize the source rocks not vertically but laterally for deciding on the location of the horizontal wells. And what better to pick up than the seismic data here? So the determination of TOC directly from the seismic data is a difficult task, but it can be attempted indirectly, as we describe in this case study. Now we know that TOC influences the compression velocity, shear velocity, and the density of the material. So it should be possible to detect the changes in TOC from the seismic response. Additionally, there is evidence of a linear relationship between the uranium content in the shale and its organic content. So as a result, a large gamma ray response is expected for organic rich shale formations. And we should be able to identify the source rocks with the help of GR response. Now, as I mentioned earlier, the P impedance and the gamma ray are two important parameters for identifying the source rocks in terms of the TOC. While P impedance can be determined from the different available methods of impedance inversion, there is no direct way of computing gamma ray from the seismic data. Yes, we can use extended elastic impedance, because it provides a way of computing this TOC from the seismic data, but for that we need pre-stack data, and we were only given the post-stack data for this purpose. So neural networks, they make it possible to predict suitable petrophysical properties such as porosity, gamma ray, water saturation away from the well using a non-linear type of relationship between seismic data and different derived attributes with petrophysical properties. Now, with this background, we attempted to characterize the VM formation by way of a feasibility study on post-stack seismic data. Now, I have to mention that Loseth and others from Statoil in 2011, they had, in a similar presentation at the SEG, they had demonstrated that acoustic impedance decreases non-linearly with increasing TOC percent. This relationship was then used to transform a seismic acoustic impedance volume into a TOC volume. So that was our starting point. So we cross-plotted the P impedance against TOC values and color-coded them with gamma ray, as you see here, and just to see if there is any kind of relationship. Now, the TOC values were obtained from the log curves calibrated with core measurements, which look good, and the cross-plot is, as you see up here. Now, it appears that both a linear or a non-linear relationship could be a reasonable fit to the data points. But the important point to note here is that whichever relationship we use, the high TOC interval will remain underestimated both ways. And at the location of the arrow that I show there, there is a limitation. This is a limitation of the Loseth et al. Approach. And predicting TOC only based on such an approach would have an inherent uncertainty, and so was not considered advisable. But on the cross plot, we do notice that there is a correlation between gamma ray and TOC. So high gamma ray it does show us high TOC. So we cross-plotted the P impedance against gamma ray and color-coded it with TOC as shown on this slide. I go back and forth, and you see that this is a much better relationship than the previous one. High values of TOC and gamma ray are characteristics of a better quality shale play. And so we enclosed some of the points that I show here in red with the polygon and back projected them on the vertical log curves. We notice that most of the points enclosed in the red polygon, they are coming from the deeper reservoir zone as expected, suggesting that the P impedance and the gamma ray can together be used to differentiate between the deeper and the shallower part of the reservoir. But such a differentiation would not be possible based on the TOC estimated from the P impedance using a linear or a non-linear relationship. Even if differentiation were achieved, uncertainty would still exist in terms of the quality of the shale. So next step was to account for the uncertainty associated with the characterization of the VM shale, and we used a Bayesian classification approach for generating a facies model. To do this, first we defined different facies based on cutoff values of gamma ray and P impedance. With this information, we defined probability distribution functions using Gaussian ellipses. These are shown on this particular slide to the left. 3 facies were identified: facies 1 in green, facies 2 in dark green, and facies 3 in red. And based on the P impedance and the gamma ray values, the quality of the shale must increase from red to green color. Projecting these values on the log curves, we notice the quality of the VM formation increases with the depth, which is reasonable based on the geological history, as I had mentioned earlier. So next we generated the P impedance from the seismic data using model-based inversion, and this is a standard workflow for doing so. And the one thing that we focused our attention on is the generation of the low frequency model, and I won't go into the details of this because this is pretty standard. Now the usual way of generating a low frequency model is to use a single well, low pass filter the acoustic impedance log, and constrain the impedance values laterally using the interpreted horizons on the 3D volume. And that would be something on these lines. We pick up this a single line passing through the low frequency model that has been generated. The problem with this approach is that if such a model is used in the impedance inversion, it may not match at other locations. And as you see here, I'm showing you a number of a number of low pass filtered curves for density and P impedance. The inversion analysis that we carry out for such a low frequency model generated, it tells us it demonstrates that at the location of the well, the inverted trace on the left hand side, as you see, that is the inverted trace in red, and the impedance log trace is in blue. And the two traces, they match at the location of the well, because this is the well that is being used for generating the low frequency model. But on the right hand side, you see there is a mismatch at the location of the indicated arrow, and the red trace, it deviates from the blue trace, which is the measured impedance trace. The red traces are the traces that you see or that are generated from the inverted trace, and the blacks are the traces generated from the seismic data traces. And the error is obviously small, but we still have deviations in terms of the log curve correlation. And so the other approach is to use the multi-well low frequency model, and using an inverse distance weighted scheme or a process such as the kriging, and that can generate a low frequency model. Such models suffer from artifacts in the form of bullseye type of artificial tongues that can create artificial anomalies on the impedance volume. So instead of using these, we used a multi-attribute regression approach, where we make use of well log data as well as various seismic attributes to obtain a relationship between them. More details on this approach will be shown in a presentation on Wednesday. But I will mention here that the output from this approach is a more laterally harmonized low frequency model that is free from artifacts. And the workflow I demonstrate here. Now to show, to demonstrate what what effect this will have on the final results, here we have a horizon slice average over a 10 millisecond window above the base of the VM formation. And notice the distribution of the impedance on this display, which has been extracted from the impedance generated with the low frequency model derived from a single well. The equivalent impedance display from the impedance model generated with the low frequency model derived from the multi-attribute regression approach is given here. And as I go back and forth, you will notice that there is a change in the values. And usually, if you look at the range of values that are shown to the left here, 8177, and then you have 10,000 something, and compare these with the values that you see here, 10,507 here and 8300 here at the lower end. You see these values are different. So what we do is we display it to the same range. So both the low frequency model generated from a single well and that generated using a multi-well regression approach, they are now displayed on the same range of values, and notice these values are high, high impedance, and similarly here, and that is not what was expected. The Now, if we show the TOC that has been calculated from these volumes, because that is what we derived from the use of the neural network approach, and I will come back to this a little later. You see here, this is from the single well, and it should be high TOC, and this is a high TOC display. So a similar display when the impedance was derived using this high impedance, using the multi-regression approach is seen here. And so there are problems with the single well low frequency model, and that is what we wanted to eliminate. Now here is an arbitrary line from the impedance volume passing through 5 wells that we see here in the inset. We have 1, 2, 3, 4, and 5. So these are the 5 wells passing. I mean, this line is an arbitrary line passing through these 5 wells and passing through the passing through the impedance inversion. And notice we have lower values of impedance all through, which is representing the VM formation. And here is the other arbitrary line passing through the other 3 wells. That these are the 3 wells, 6, 7, and 8 here. And again, notice the same thing. The top of the VM formation and the base of the VM formation are shown clearly on the left and the right hand side. Now, based on the neural network approach, we calculated, or shall I say, we predicted the gamma ray as well. And here I show the computed gamma ray volume, the data from the computed gamma ray volume, and from the actual gamma ray value at the location of the different wells, and you see here a good correlation between the two. Similarly, I show here a log panel where we show the match between the gamma ray curves at different wells and the predicted gamma ray curves with the neural network approach. The yellow bars show the zones over which the predictions have been made, and you see they are pretty good. The match is reasonably well. Next, the probability density functions derived from the wells were used to derive the facies volume, and of course these had to be tweaked because now we are using the probability density functions on seismic data. But the point is that the facies that we are talking about here, that they are the green, the dark green, and the red facies, and a small segment of the line is shown here. Apparently the green facies at the bottom is much better, and the facies changes to dark green and red to the shallower part. So far the facies that we have derived are in terms of the 3 colors, and their separation gives us an idea of how they are distributed in a vertical and a lateral sense. We can take this forward by generating the facies probability volumes for the broad zone of interest with the use of the PDFs. The advantage of using the PDFs is that they are intuitively easy to understand, and also the fact that the uncertainties in the data and those that result from inversion are due to the limited resolution. They can also be looked at. Such uncertainties result in overlap of the PDF displays. So using the PDFs derived from the well data and tweaking them a little bit, the probability volumes were computed for the different facies derived earlier, and I show the equivalent segment of the line here. High probabilities of occurrence of the green facies is seen, which is quite encouraging. Here is a horizon slice taken 8 milliseconds above the base of the formation, and facies 1 in green seems to dominate, and of course with the distribution of the dark green and the red facies is also shown here. An equivalent horizon slice from the probability volume for facies 1 is shown, with a probability of occurrence of 85% is seen. I mentioned about the faults and fractures being associated in the VM formation. So we generated the discontinuity volumes also, that is coherence and curvature. But because we are close to a very coherent reflector, the coherence did not help so much, and so we are displaying the lineaments from the most positive curvature, and we have used transparency to show these lineaments in black. So on this display I show a horizon slice on the TOC volume 8 milliseconds above the base of the VM formation, and overlaid on this display is the most positive curvature attribute, as I said. Now these lineaments in black are indicated with the yellow arrows in the middle, as you see there, or shall I say an orange arrow. Now these events are interpreted as the Aeolian events associated with the mega dunes, and we won't go into the details of that interpretation here because that is not relevant to what we are trying to show. And in the background, in the colors, you see the TOC content. So it shows a reasonably good distribution of the faults and fractures that we have in the area. And finally, the conclusions to this case study are the results of this feasibility study look very encouraging and opens the door for more detailed work that should be done, probably using the pre-stack seismic data. The TOC computations based on linear or non-linear relationships with acoustic impedance from the log data and the TOC values could have some inherent uncertainty and may not be suitable for use. And in this work we have demonstrated the potential for application to other shale plays around the world. And finally, I would like to say this. The geology of the Nukan Basin is favorable. The VM formation is thicker than most similar formations around the world, and thus production can be enhanced by drilling from a single location. As more and more wells are being drilled, the budget, or shall I say the drilling budgets are shrinking, and according to a recent report from YPF, the cost per well has shrunk from $11 million to $7.5 million. And with companies like Shale and Total and Chevron and others that are working in the area, the future outlook looks promising. Now, when it is looking so encouraging, you think the name Vaca Muerta, which means a dead cow, is relevant. Is it? I don't think so. They should call it Vaca Viva, or a living cow, which the Argentinians can milk for the next several decades. And so with this, I close my talk here. And with this, I thank you for your attention.